Welcome to Study Loop.
In this problem, we're going to talk about ideal gases. We're going to start with the ideal gas law. So P times V, so the pressure times the volume of the gas, is equal to both constant K times the number of molecules M times the temperature of the gas. Also, for an adiabatic process, P times V to gamma, where gamma is the adiabatic index, is equal to a constant. I'm going to call this constant C. Also, we're going to need to remember that the derivative of the pressure with respect to the y-coordinate is equal to minus the density of the gas, rho, times g. Okay, so our going question A is to use these equations to show first that P uh, to the 1 minus gamma times t to the gamma is equal to a constant. I'm going to call this constant g. And then we have to show that minus 1 minus gamma rho g plus rho p over t times dt dy is equal to 0. Okay. So what I'm going to do is to start with the adiabatic equation. Then I'm going to use the ideal gas law to isolate V. So I have that V is K and T over P. Then P times V, V is K and T over P to the gamma is equal to C. Then P to the 1 minus gamma times T to the gamma is equal to C divided by K n to the gamma. I'm going to call this D. Okay, so P to the 1 minus gamma times T to the gamma is equal to D. And I'm going to differentiate on both sides. So with respect to y, notice that the right-hand side is constant. The left-hand side is 1 minus gamma times P to the minus gamma times T to the gamma times the derivative of P with respect to y. I'm using the multiplication rule, plus gamma times C to the gamma minus 1 times P to the 1 minus gamma times the derivative of T with respect to y, and this is equal to 0 because the right-hand side is a constant. Okay, then I'm going to use that dp dt, I'm sorry, dp dy is equal to minus rho g, and also I'm going to divide both sides by 1, by p to the minus gamma times c to the gamma. So what we obtain is 1 minus gamma times dp dt, that's minus rho g, plus gamma times t to the minus 1 times p, so that's p over t, times dt dy is equal to 0. And this is exactly what we wanted to find. Then in question B, we have to show that the derivative of the temperature with respect to y is equal to 1 minus gamma divided by gamma times the average mass of a molecule times g divided by Boltzmann constant. So what I'm going to do is to start with the equation we found in question A. So what we have is that delta t, dt dy is equal to 1 minus gamma times rho g times t over p. Now notice that PV is equal to K and T. This means that T is equal to PV divided by kn. So dt dy is equal to 1 minus gamma times rho g pv divided by p kn, with p's cancel out. And notice that rho, the density times the volume, is equal to the mass. So this is 1 minus gamma times the mass times g divided by k. Times n, and actually this is the total mass. Instead of writing it as lowercase m, I'm going to write it as capital M. This is the total mass of the gas, not the mass per molecule. But notice that the mass per molecule, lowercase m, is the total mass divided by the number of molecules. So now we can say that this is 1 minus gamma. Actually, there's a gamma down here. Divided by gamma is times mg divided by k is dt dy. This is what we wanted to find. Then in question C, we have to consider that the average mass of a molecule of air is 29 atomic units, U, and the air is a diatomic gas, so gamma is 7/5. This is true for any diatomic gas in normal circumstances. Also, K is 1.38 times 10 to the minus 23 meters squared kilogram per Kelvin second squared. And our goal is to find dt dy in this situation. So dt dy, according to question B, is 1 minus gamma divided by gamma times m, that's 29 times the atomic mass unit, that's 1.67 times 10 to the minus 27 kilograms times g, that's 9.8 meters per second squared, divided by k, and that is 1.38 times 10 to the minus 23 meters squared kilograms per Kelvin second squared. So dt dy is minus 0.0098 Celsius per meter. Now if I multiply and divide everything by 1000, I obtain minus 9.8 Celsius per kilometer. Then in question D, our goal is to calculate, is to consider that the initial temperature, the temperature at the top of the Sierra Nevada mountains is equal to minus 5 degrees Celsius, and the height y of the Sierra Nevada mountains is 4,000 meters. And our goal is to find what should be the temperature at the Death Valley, which is located at minus 100 meters. So notice that the temperature Tf, actually the temperature T0, this is the temperature at the top of the mountains, is equal to the temperature at the bottom plus dt dy times delta y, where delta y is y0 minus yf. So our goal is to find Tf, so I'm going to isolate it. So we have Tf is equal to T0 minus dt dy delta y. T0 is minus 5 degrees Celsius, minus dt dy is plus 9.8 Celsius per kilometer. times 4,100 meters, that's 4.1 kilometers. So TF is equal to 35 degrees Celsius, which is the answer to our exercise.